All right, our next topic now is the Gaussian or the normal distribution, which in many ways is the most fundamental and most important distribution in all of statistics. And is one that a lot of, well, somehow a lot of statistics applications involve the normal distribution for reasons we'll see later in the course. But for now, we're going to record the basic properties of the normal distribution. So most people call it the normal distribution. Gaussian distribution is the same. So a random variable z has the standard normal distribution if it is a continuous random variable with density as follows. So it's 1 over square root of 2 pi. That's just a normalizing constant. E to the minus z squared over 2. And this is for all values of z, real numbers, positive and negative. This is sometimes also written as lowercase phi of z. That's a reserved notation in a lot of textbooks for the density of the standard normal distribution. Okay, so what does this look like? This is the bell curve. So this is the famous bell curve. And the way it looks is pretty much like this. Okay, so see how many tries it takes me to get a good looking bell curve. It's actually not bad. It's not great. It's not great. But it's not bad. So what is the let me try it one more time. Oh, man. Almost. Okay, so what are the properties of this? So properties are that within between -1 to 1, there's 68% probability. Between -2 to 2, there is 95% probability. And between -3 to 3, there is 99.75% of the probability. So almost all of the probability is between -3 and 3, even though this is a distribution on all real numbers. And so this is the distribution that we get when we take an average of a large, well, by the central limit theorem, this distribution we get when we take an average of a large size sample. And these numbers have a pretty straightforward interpretation as follows. So let's calculate, let's see if we can calculate the expectation of z. Okay, so how do we do this? Well, by definition, right, it's integral minus infinity to infinity of z times the density, 1 over square root of 2 pi e to the minus z squared over 2 dz. pull the 1 over square root of 2 pi out. Well, first of all, you might want to have a guess at what the expectation is. The obvious guess would be that the expectation is 0 because this distribution is symmetric around 0. So just first observe phi of z is equal to phi of minus z for all z. So if it has an expectation, it has to be 0. The question though is, does it have an expectation? So it is possible that this would not have an expectation if the positive and the negative parts were both infinity. Okay, but this can be integrated by parts. Right, so if we integrate by parts, we would say u is equal to, let's say, z squared over 2. Du is equal to z dz. And we would be left with 1 over the square root of 2 pi e to the minus u du. And we would break this up into the, well, in this case, u would also go from, so we'd have to break this up into 2 parts first, but we would do that. So this is equal to negative part and positive part. So negative infinity to 0, z e to the minus z squared over 2, plus 1 over square root of 2 pi, 0 to infinity, z e to the minus z squared over 2, dz. And then we do the u substitution. Sorry, it's not integrate by parts, u substitution. So we get well, now it's going to be integral from infinity to 0 of e to the minus u du plus integral from 0 to infinity of e to the minus u du. So obviously those are the same integral, but with the reversed limits of integration. So that equates to minus 1 over square root of 2 pi, 0 to infinity, e to the minus u du, plus 1 over the square root of 2 pi, integral 0 to infinity, e to the minus u du. You might ask why I didn't just write it as 0, but I have to verify that the integral is finite first. And it is. This is just 1, actually. If you were to work out that integral is 1. But at this point, just do it. So 1 over the square root of 2 pi outside. Antiderivative of e to the minus u is minus e to the minus u. Infinity 0 is just 1. It's going to equal 1. And then same thing here. It's going to be e to the minus u. Infinity to 0 is going to be minus 1. So it's 1 over the square root of 2 pi, 1 minus 1, which is of course 0. Okay. So the expectation is what we expect it to be, 0. But we had to be a little careful. The variance of z is expectation of z squared minus expectation of z, the quantity squared. Okay. Which we know that that's just equal to the expectation of z squared because expectation of z is 0. Okay. So this is integral 1 over square root 2 pi. Well, integral z squared 1 over square root 2 pi e to the minus z squared over 2 dz. can integrate this by parts. But to do that, we would break it up like this. We break it as z times z 1 over square root 2 pi e to the minus z squared over 2 dz. So this would be dv. Yeah, this would be u. This would be dv. Okay. So when this is dv, we have to take the antiderivative, right? So u is z, du is dz, v is z times phi. Let's write it that way, dz. I'm sorry, dv. And then v is going to be minus phi of z. Okay. So then what we do first is it's uv, right? It's u times v. So it's z times the negative of phi. E to the minus z squared over 2. Limits are minus infinity to infinity, and then we subtract off integral of v du. Du is just dz, so it's just integral of minus e to the minus z squared over 2 pi. Okay, what does this equal? Well, this integral here is 0 because e to the minus z squared is 0, and that's way, we have to take a limit here technically of integration, but that's going to outlast the z, which is being put as in as infinity. So this is going to be 0. This is minus minus, so it's plus integral minus infinity to infinity of this piece, which is actually just the density, and we know that densities integrate to 1, so this is just 1. So we have mean 0, variance 1, and therefore also standard deviation 1. Okay, so that's where when we look back up here, what this is saying is in the Gaussian, the random variable is within 1 standard deviation of its mean, right? The mean is 0, standard deviation is 1. So plus or minus 1, within plus or minus 1 is 1 standard deviation of the mean, 2 standard deviation of the mean, 3 standard deviation of the mean. So the random variable is within 3 standard deviations of the mean with very high probability almost every single time. And what calls this a standard normal is that it has mean 0, standard deviation 1. So we talk about it in standard units, a standard unit being 1 standard deviation. Okay. There's some common notation. We've already talked about it. So common notation is to define lowercase phi as the density. And then when we do that, capital phi, these are Greek letters, capital phi of z is defined as the distribution function of z. So this is the cumulative, these are the cumulative probabilities of the standard Gaussian. And then if you have a value alpha between 0 and 1, then z alpha is written as the number such that the cumulative probability is alpha. Okay, so this is the alpha quantile. So for example, z 0.5, well, where is the value at which the cumulative distribution has 50% probability? Well, 50% of the probability is to the left of 0 and 50% is to the right. So that value is 0. Z of 0.84 is equal to 1. That's this point here. And then Z of 0.025 is -2. Okay, so 0.025 is having 2.5% to the left. That would be all the way over here. Now, from the just like we did for the uniform 0,1, where we said, okay, we have a uniform 0,1 on the unit interval, but in general, we want to generalize a family of distributions from this. And the way that we did it was through transformation. Okay, so a random variable x has the normal distribution with parameters mu and sigma squared, and it's written as x distributed normal mu sigma squared if z, which we define as the normalized version, so we subtract the mean and then we divide by the standard deviation of x. If this is a standard normal random variable, then x is a normal random variable with those adjusted parameters. Okay, so or alternatively, we let z be normal 0, 1, which is standard normal. So standard normal has parameters 0 and 1, and define x as sigma z plus mu. Then x is still in the normal family, but has parameter mu and sigma squared. Okay, and this is for values. So this is for mu can be any real number. Sigma squared has to be positive. Okay, so this is what's called. So this is called a change in scale and location. Oops. This is a change in scale and location. We are moving the distribution to be centered around mu, and we're scaling the distribution. Okay. And because of this, what can we say? Well, we can rederive the density, the distribution function, and everything like that. So the expectation of x, so let's let x be mu sigma squared, then we can write x. So by definition, we can write x as sigma z plus mu for a standard normal random variable z. So then from this, we can immediately calculate things like mean and variance of x as follows. So expectation of x is equal to the expectation of sigma z plus mu. Okay. How does that work? Well, we have linearity of expectation. So this is sigma times the expectation of z plus mu. Expectation of z is 0, so sigma times 0 is 0, so we're left with mu. So mu is the expectation of x, and the variance of x is variance of sigma z plus mu. Mu doesn't factor into variance, so it's just sigma times z. Sigma comes out as a square. It's sigma squared times the variance of z. Remember, variance of z was 1. So variance of x is sigma squared. X has a density. Okay, now how do we figure out the density in this case? Well, we can do it in a couple of ways, but there's a pretty, we talked about the infinitesimal approach before. The infinitesimal approach would be to say, if I have a random variable with a density, remember, then the value of the density can be thought of as taking a very, very small window around X and realizing that the area under this curve here is pretty close, and in fact will be exactly the same as the area of the rectangle that we get by adding this piece up here. So there is error, but it's approximately the same. So in other words, if X has a density, what is it? The density is, so this would be, so what's the area of the rectangle? Area to rectangle, whatever the density is, call it f of x, is fxx, that's height. So the height of this is fx. Well, the height of, I'm sorry. Yikes. Okay. So the height of the rectangle is inside. It's the smaller rectangle. And then there's that extra piece, right? Because this value here is f of x. Okay. But it's so the area of that rectangle there, that red rectangle, is the height f of x plus times the base, which is x plus dx minus x, which is dx. So this is f of x dx. Okay. But we know that if we have small dx, it's reasonable to approximate this, that this is a reasonable approximation to the probability that x is between, the random variable x is between x and x plus dx, because that's what the area, that's the area under the curve. So we don't know anything about how to do this directly, except through how we transform this random variable x to get a standard normal, standard Gaussian. So we subtract off mu and we divide by sigma. We know that if whatever we do to one side, we have to do to the other. Okay. Sigma is a positive, so we can do that. Sorry, this is x plus. Okay. Okay. But now we know that x minus mu over sigma, that's the standard normal. Okay. And then here we're x minus mu over sigma. Here we are x minus mu over sigma plus dx over sigma. But now this is saying, this is the probability that a standard normal is between x minus mu over sigma and x minus mu over sigma plus dx. Well, it's the same calculation. It's the same way to approximate, except up here, instead of being f and x, it's the f of z. It's phi, the normal, and it's evaluated at a different x. So this is by the way we do the approximation. It's the height, the density, evaluated at x minus mu over sigma times the width. The width here is dx over sigma. Okay. But what is that? Well, we just plug into the, so it's dx over sigma. And let's just isolate the part that doesn't include dx, right? So on the one side, we have f of x dx, and on the other side, we have something in terms of f of z dx, right? So this piece here has to be the same as f of x. So the distribution of the normal with mu sigma and mu with mu and sigma squared is 1 over sigma times f of z, which is 1 over square root of 2 pi exponential minus 1/2 z squared, which is x minus mu over sigma squared. So the way it's usually written would be minus x minus mu squared over 2 sigma squared. And this is for x between any value between minus infinity and infinity. There are many applications, many ways to use the normal distribution. We're going to see several of them throughout the course. What I can say, what we'll go through right now, for example, are a few observations that we'll discuss later on. First one, and one of the most direct uses of the Gaussian distribution is for estimating the binomial. So the normal approximation to the binomial distribution so how this works is, well, if x is binomial n and p, then x is approximately normal np npq, provided npq is bigger than 10 or so. And this is something that we will make heavy use of throughout the course. And that, beyond this course is something that comes up all the time. And we'll go through some examples of this starting in the next class.